So in this lesson, we're going to extend the work that we've done on area from the previous lesson to the idea of volume. So we're adding a dimension here, and we're doing so in what I think is a pretty cool way. Just to remind ourselves what volume is, we're going to consider this cylinder here, and we're given the cylinder has a radius of 2 and a height of 5. If we're asked for the volume, we're really talking about like how much stuff would fit inside this cylinder, right? So we have a formula for most shapes. In this case, the volume of a cylinder is pi r squared, which would be the area of the base, and then times the height, which we're given here is the height. So one way you can think about this formula is we're taking a circle that is the base, and then this height variable measures how many circles do we stack on top of themselves to get the whole cylinder, right? So the work here would just be very trivial, right? So my r is 2, so r squared is 4 times 5, and we could leave it as 20 pi. And that's usually how we're taught this stuff. We're just like given a bunch of formulas and told like this is how we find the area of a cylinder. These formulas actually come from calculus, and actually some of the first work trying to work with the number pi is some of the earliest work with limits that was ever done in the history of mathematics. So as you go on in your calculus career, you may start to understand where these formulas come from. Let's move on to something similar to what we covered in the last lesson. We have this region R bounded by the lines, some horizontal and vertical lines on the y-axis. So here's my region R, so you can label it and shade it in. Kind of an unfortunate color combination here. And what we're asked is, what is the volume of the solid created when R was rotated around the x-axis? Here's where we have to start to use our imagination a little bit. So here's the x-axis, right? We're rotating that region around. And what we'd actually get, if you imagine like a rectangle spinning around, is we get a cylinder. And draw it as best you can. I'm struggling because I'm drawing on the computer. So we get a cylinder if we took that rectangle and we spun it around. So really we're asked, what's the volume of this cylinder? Well, notice my radius again is 2. And my height again is 5. From 0 to 5. So we know my volume should be 20 pi. But we could actually write this as an integral if we wanted to. So notice we have an x value. We have the integral from 0 to 5 then, and we have this curve 2. So right now we just have the region R, the area of the region R. If we kind of follow this formula that we used before, R was our radius, right? So what if I do 2 squared, and if my formula is pi r squared times the height, I maybe want to throw a pi in front, right? So here's pi. Here's my height is my integral, and then my r squared is the function that I'm using. And let's integrate this and see what we get. So my pi can just kind of chill out, and the integral of 4 is, of course, 4x. And then if I plug that in, I get pi times 4 times 5 minus 4 times 0, which of course would give me 20 pi again. Okay, so I can use calculus to create a cylinder from a graph, and then the results I get, if I kind of convert my volume formula into an integral, is the same as what I would expect if I did it in our kind of baby geometry way. What's kind of interesting to me is each piece of my integral kind of represents a part of my volume formula. So pi obviously is pi. Here's my height is the integral. And here is my r squared is my curve squared. Okay. Now we can consider trickier problems with this is why it's useful to learn this. Otherwise, why would we ever do anything besides my geometry formula, right? So here we're asked, what do we get when we rotate the region around y equals -2? So that would be this line. So notice we're taking, again, this region R, but this time we're rotating it around something different. So if I'm rotating around that line, y equals -2, I would come probably all the way down to -6 down here and go back up. But notice we have this empty space here between the region and what we got, right? So we would also have sort of an inner radius. So what we get is sort of this donut-shaped solid, right? So it's a cylinder with a hole in the middle. And I can kind of fill it in, right? And I'm not going to shade it, but you can imagine on the inside, we'd have this hole. So obviously the math here is going to be a little bit more complicated, but we can still use a similar idea, right? So we want the integral from 0 to 5. We're still going to use pi. And then my radius this time is going to be 2 minus negative 2. And that comes from, we have this line y equals 2. And then we have this y equals negative 2, right? So it's the distance from the curve to the axis of revolution. I'm going to square it. But now I have to take away that inner piece, right? So the inner piece, I'm going to say, is from 0. So that's now this line, right? The inner radius minus negative 2 squared dx. And these are, again, this is math that I could do using my geometry formulas, but we're building towards being able to tackle more complicated situations here. So we get 16 minus 4. So 5 times 12 minus 0 times 12 is 60 pi. And what's cool about this is if I took pi r squared times the height to get my outer cylinder, and then I did the same for my inner cylinder and subtracted the two, I get the same result. Now, really why we're learning this method is to tackle a problem like this. So now we have two curves being revolved about the line y equals 4. I'm going to draw a picture real quick. So I happen to know that f of x looks like this. And g of x is just a line. And here is our region R. Now, we would want to find this intersection point. That intersection point happens at x equals 4. And you know how to find that at your calculator at this point. And then there's another intersection at x equals 0. You could also solve the equation here for your intersection. And then we're asked to revolve about the line y equals 4. So that would be up here somewhere. Right, y equals 4. Okay, so we're going to follow the same steps as we did for our easier problem, right? We're going to do the outside curve, outside radius minus the inside radius squared. Well, my outside curve is the one further away, so that's g of x. So it would be the integral from 0 to 4 times pi. Then we'd have g of x minus 4 would be the distance squared. By the way, this order doesn't matter because you're going to square it anyway. Minus the inside curve, which is f of x. Okay. So this is my outside radius. This is my inside radius. And now I can substitute those functions. And now you could do this by hand. So I'd square both of these binomials, multiply them out, and then integrate each term, then plug in 4 and 0, then distribute my pi. But at this point, I'd be reaching for my calculator. It probably had you scared for a second there, right? So I would do math 9, include the pi, and this would give me a decimal. I'd write it accurate to 3 places. So 25.13. And what this would look like, and I would love to see you making sure you can imagine some of these. What this would look like is sort of like our cylinder we saw before, but obviously gets kind of shorter and skinnier as we get out towards the edge. So that's why this method is really powerful, because it allows us to consider more challenging shapes like this. Let's write down the general method. So the volume of a solid from A to B is just the integral from A to B times the outer radius squared minus the inner radius squared. And this is often called the disc or washer method. Sometimes these are taught separately, but it's really the same thing. So in our first examples, we had no inner radius. So sometimes that inner radius is 0. But that is the setup. The most challenging thing is going to be figuring out what your inner and outer radiuses are. So you can make a note that inner and outer your inner radius is the function. The most common error or the most common challenge is figuring out what the inner and the outer radius is, right? So our inner radius here was f of x because it was closer to y equals 4. Our outer radius was g because it was further away. So it's like, what is the outside shell of this shape? So you can add this note here if you think it would be helpful.